First of all, a very warm good morning, ladies and gentlemen. This is Kaushik Mishra, a faculty of Computer Science and Engineering, SUIIT Bulla. The topic of my presentation is Design of Intelligent Scheduling Algorithms for Cloud Computing. So let's quickly run through the outline of this presentation. So these are the outlines of this particular presentation. Next, that I would like to define the cloud basically. So the basic, very scientific definition of the cloud computing goes like: the cloud is a market-oriented distributed computing system consisting of a collection of interconnected and virtualized computers that are dynamically provisioned and presented as one or more unified computing resources based on the service level agreements established through the negotiation between the service provider and the consumers, especially. And the words that are highlighted in the red ink, those are the features of the cloud computing. Basically, in the cloud computing, we have the set of the cloud service models through which the cloud services are going to be delivered to its cloud customers. So based on that, we have your three set of the service models. The first one is called software as a service, number two is called platform as a service, and third one is called infrastructure as a service. And in this cloud computing as well, we have a few set of the cloud deployment models as well. And based on that, we have this public cloud, private cloud, and the third one is called hybrid cloud. Next one that I would like to define you this cloud task scheduling as well as this particular load balancing. So the key idea behind this task scheduling algorithm is the optimal assignment of the task with your particular compatible VM so as to achieve the following goals. That means high throughput, improved performance, minimization of the execution cost, as well as the power consumption, and we have a high degree of the efficient utilization of the VMs as well. And the key idea behind this load balancing algorithm is that we have to improve the quality of service parameters by simply dispersing the loads uniformly across the VMs. And this particular algorithm has to be executed before any task scheduling algorithm in order to alleviate the performance of this particular system. And the motivation of this particular research is that on a daily basis, your humongous amount of data is being generated from every walks of life. So therefore, it is utmost important to process those data within a predetermined time. And hence, the advent of the cloud computing has paved the way to be a viable option for balancing the load as well as this scheduling of the task. And since the nature of data is quite dynamic, independent or dependent, and non-primitive in nature, cloud computing appears to be a prominent and the promising solution as it offers a virtualization technology for this dynamic scheduling of the cloud request as well. So hence, this particular contribution focuses on developing some set of the efficient scheduling algorithms as well as use load balancing algorithms in order to address this particular solution. So therefore, this particular research designed some of the improved meta-heuristic as well as this hybrid algorithms in order to propose, and mitigate the aforementioned challenges as well. So these are the set of the papers that we have taken into consideration for carrying out this particular research. Next one is that I would like to talk about the system architecture and the problem formulation in the cloud computing, that we have taken a set of the tasks that is your independent and the dependent task that is expressed in the million instruction basically. So in order to process those tasks, we have taken a set of the VMs basically, that VMs are called as the virtual machines out of this physical machines, and the speed of this VMs is expressed in MIPS. So for this matter, I have also taken some of this quality of service parameters in order to assess our proposed, that this meta-heuristic or this hybrid algorithms as well. So first one, that we have formulated our task into the VMs with a two-dimensional matrix basically, and that two-dimensional matrix is being represented with Xij. Xij is equal to 1 if a task is assigned to the VM, and if 0, otherwise. And for that, your completion time for each and every task is also calculated using equation 2. After that, we have calculated the make span with using equation 3, and then the utilization of all the VMs and the average utilization are also calculated using equation 4 and 5, along that with the response time is also calculated using equation 6. Then we have calculated the capacity of each and every VM and the overall capacity of the VM, and then are calculated using equation 7 and 8. After calculating the capacity, we have also calculated the load, overall load, and the total load, using the equation 9, 10, and 11. With calculating the load, we also need to calculate this particular processing time, and that can be calculated using equation 12 and 13. After calculating the load of each and every VM, now our task is to state or classify the VM into a set of the group. So based on the load of each and every VM, a VM can be classified into either you this underloaded VM or this overloaded VM, or you this normalized VM based on equation 14. Then after calculating the load, now that we have to take the load balancing decision. So for that particular load balancing decision, at first we have to calculate that whether our system is balanced or not. So in order to check that, we have a particular standard deviation is there, and that can be calculated using equation 15. And the value for this particular standard deviation can be compared with a threshold value. And if the value of this standard deviation is greater than that particular threshold value, and then the system will be identified as imbalanced and your desired load balancing mechanism can be triggered. So in order to check that whether a load balancing is possible or not, so for that purpose we have to check that whether the entire load or the total load is greater than the capacity of all the VM, then the load balancing is not possible. And next, and otherwise we have to trigger the load balancing decision. Then after that, we have also calculated the degree of imbalance. It can be calculated using equation 16 and 17. And this degree of imbalance is a kind of its barometer in order to find the imbalances of tasks among the VMs. So after calculating the load and after stating the VM group, basically now our task is to migrate the task from that that overloaded VM onto this underloaded VM. So for that purpose, the first thing is that we have to calculate the total resources used and the total resources available of all the underloaded VM, and that can be calculated using equation 18 and 19. After calculating this, now our task is to calculate the cosine similarity and the compatibility value of all those tasks of this overloaded VM with that underloaded VM. So for a particular pair of the task with its underloaded VM, if the compatibility is greater or better, now that's the thing now that we have to migrate the task from that overloaded VM onto this underloaded VM basically. So this is the load balancing algorithm. The steps that I have explained here, all the steps are being formulated over here. So sort of the VMs means what? That we have to sort the underloaded VM in the ascending order based on their respective loads basically. And if the loads of two underloaded VM are same, now we have to rearrange that underloaded VM in the descending order based on their VM utilization. And next, that we have to sort the OVM in the descending order based on the loads, and based on the compatibility and the cosine similarity, we have to simply transfer or migrate the task to the most compatible underloaded VMs. So for this matter, we have also proposed fitness function, and this particular fitness function consists of three objectives. The very first objective is that we have to minimize the make span, and at the same time we have to maximize the resource utilization, and it is formulated in the equation 22. Our second objective states to minimize the load balancing, and it is formulated using equation 23. Our third objective is all about minimizing the power consumption, and it can be calculated using equation 24 and 25 basically. And next one, that to formulate the proposed fitness function, that we have taken the weighted average of all this particular fitness function together, and for that we have taken three set of the weights, W1, W2 and W3, and those weights are the difference in the mix span, VM utilization, and the total energy consumption, respectively. So next slide is all about your intelligent meta-heuristic and the hybrid scheduling algorithms. In this section, first, that we have proposed a modified particle sum optimization, or that Npso algorithm. This Npso algorithm differs from the basic PSO in two ways. At first, your scalar quantity is used for the particle speed instead of the particle's velocity, and the number two is called a rule is used to update the position, basically. So particles speed and the particle's position are arbitrarily introduced using equation 27 and 28, and after that the particle's position are being updated using equation 29. And this is the proposed Npso based task scheduling algorithm. At first, each and every particle has to be evaluated based on a fitness function, and then after that we have to specify the p based and the global based, and if the current fitness value is less than the personal base, then we have to set the current fitness value as a new p base. And for all the particles, we have to calculate the speed using equation 29. If the speed does not belong to speed of that one particle does not belong to either S mean or X max, then we have to update the speed of that particle using that particular following equation, and then we have to update the particle's position using this two following equation, or using the sigmoid function in order to convert the continuous solution into your discrete solution, basically. And we have to repeat these steps until the maximum termination criteria is not met. Then the next improved meta-heuristic algorithm is the chaotic Joya, and this is the improvement of the basic Joya, basically. And this method is implemented in order to surmount the disadvantages of being slower the convergence rate of the standard Joya algorithm. And in this particular one, we have used a tent map function as a chaotic map function, basically, and that is defined in using 30. So this particular chaotic map function, or through this particular chaotic map function, the initialization or the particles position can be calculated or can be initialized at first. Next, the first one is that we have to set the particles dimension to the total number of tasks in the VM, and then we have to initialize the population size using this chaos map theory or the chaotic map function, and then we have to evaluate the particles based on this particular fitness function. And if the current fitness function is less than the best of phi, then we have to set the new fitness value as the base of phi, and for all the particles we have to create a new set of the mapping by simply calculating the position using equation 31, and then after that we have to transform our continuous solution into your discrete solution, and we have to repeat this until the termination criteria is not made. And the next hybrid algorithm is the Gaia, which combines the genetic algorithm along with the Jaya algorithm as well. In this combined approach, at first, your Gaia is used for solving the problem in the bigger cell space, whereas the Jaya is chosen for the problem in order to solve the premature convergence of GA by offering the high convergence rate and the low computational time as well. Besides, the Jaya is used because of its capability in maintaining the balance between the local as well as its global optima. At first, Jaya invokes the GA, calls the Jaya for the optimal mapping of tasks onto VMs, and next Jaya will generate the optimal mapping of task VM, and then it will be forwarded to the GA. And in the very next step, the GA will schedule the task on those compatible VMs, basically. So this is the desired flow chart for this Gaia hybrid algorithm. And so this is the Gaia based task scheduling algorithm. At first, the GA will be executed, and after that, your GA that at first your Jaya based algorithm will have to be executed in order to give a optimal mapping of the task, and after that we have to execute the GA algorithm for the possible execution of the task on that compatible VMs, basically, and we have to repeat the steps until the best solution or the termination criterion is not met. So next hybrid algorithm is all about a quantum inspired chaotic subsum algorithm, and here the principle of the quantum computing is incorporated with the chaotic subsum algorithm. Subsum algorithm is a population based algorithm, and in this algorithm, we have a solved chain basically, and in the solved chain, that means we have a solved leader basically, and we have a set of the followers basically, and that particular leader leads the solved chain or all the followers towards the food source of the particle. And here we have also used a chaotic subset algorithm, and this chaotic theory expedites the search space or the problem space in order to make a balance in between the local as well as this global optima. And in this cloud, in this particular quantum computing, that we have first a quantum population with the n number of the quantum agents is arbitrarily produced, and afterwards the current population is evaluated to a fitness function, and the best population is then identified according to that particular fitness value. The next one here, so the equation 32 states about the leader's position for that SSA, and after that your rand function is also being defined using equation 33, and equation 34 defines the follower's position in that SSA. After augmenting this particular chaotic map sequence into the leader's position in the SSA, our basic leader's position can now be updated to equation 37 basically. So this is the flow chart of this QB-CSSA algorithm. And next one that we have here, this QB-CSSA based task scheduling algorithm. And in this particular one, at first we have to execute the proposed QB-CSSA algorithm for the scheduling of tasks. Under this, we have to generate a quantum population. And then for each particle, we have to evaluate the fitness value based on the fitness function defined in using equation 26. And then we have to find out the best population among all the population. Then again, we have to augment the chaotic map value with the position of the leader solve and update the chaotic sequence. And the position of the leader solve has been augmented with the chaotic map value using equation 35. And then we have to update the position of the leader and the follower using equation 37 and 34. And in order to have a sufficient updating capability, we have to use a rotation angle basically, and then we have to generate the quantum population using the quantum gates, and then have to transform the generated continuous solution into the discrete solution using equation 38, and we have to repeat all the steps until the maximum number of domination criteria is not made or the fittest solution is not achieved. Next, we have done a binarization of all these proposed algorithms. Why we go for this particular binarization is that initially all these particular conventional meta-heuristic algorithms are designed to address the constraint as well as on-constraint optimization problem, which then raise the continuous solution. And those particular continuous solutions are not suitable enough to, in order to represent the task VM assignment in the cloud computing, because in the task VM assignment in the cloud computing, it only needs two values, that is two binary values, either 0 or 1, as we have discussed earlier. So for that particular binarization, we have used it here as a sigmoid transfer function, and with the help of this particular sigmoid transfer function, all the continuous solution generated from all these proposed algorithms are being converted into your discretized values basically. So next one is that we have applied all these proposed algorithms in the cloud computing architecture as well. So for this, we have also performed an experimental evaluation, and for this perspective, we have used the cloud sim, and we have also extended some of the classes of the cloud sim in order to meet our demand and the requirement in order to simulate, or that in order to carry out extensive simulations for this particular purpose. And for this particular purpose as well, as we have taken both this homogeneous as well as this heterogeneous environment or this VM in order to analyze the diversifying nature of the proposed algorithms, and also that we have taken your various real world benchmark data sets in order to evaluate our proposed algorithms. And for that purpose, we have taken both the dependent as well as your independent task. Next, these are the technical specification and use algorithmic parameters that are being defined in the table 1 and table 2 respectively. So our first simulation is all about this benchmark data set considering the task dependency. So this dependency among the tasks is being represented with a graph that's called directed acyclic graph, and here the task dependency plays a very vital role. So for this particular purpose, we have taken data sets, and that particular data sets consisting of this particular dependency task, and in that we have three factors basically. First, the size of that particular data set. Number two is the communication computation. Ratio is basically defining the completion time, and then we have your parallelism. That means the interdependency among all the tasks. So based on this, we have here this particular figures. So figure 2, figure 3, and figure 5 are the performance comparison over this particular data set in terms of this make span, VM utilization, and this response times basically. And then this figure 5 and figure 6 are all about this performance comparison for your this power consumption as well as this load balancing. So from all this figure, it is quite evident that the hybrid approach that QBC SSA outperforms better in comparison to other proposed approaches. Next, simulation is all about your task independent task is all about, and for this we have taken two different set of this particular data set, and then again that we have combined this particular two data set in a structure that is more suitable to our environment. And that particular structure defines your U, X, and TN. U is all about your uniformly generated data, and X defines a type of consistency, that is your consistent, inconsistent, and semi-consistent data, and T denotes the task heterogeneity in terms of high, low, and medium, and M also denotes your machine heterogeneity, or the VM, that heterogeneity in terms of high, low, and medium respectively. So for that particular purpose, we have also defined our task set into three different task sets, basically set 1, set 2, and set 3. It's all about in the form of your task into VMs. That means 1000 tasks are going to be scheduled on 96 set of VMs. So for that one, so the figure 7, 8, and 9 is all about the performance comparison over this benchmark data sets for this make span for the 3 set of the task respectively. Figure 10, 11, and 12 for this VM utilization. Figure 13, 14, 15 is all about for your this particular response time. Figure 16, 17, 18 is all about for power consumption, and figure 19, 20, and 21 is all about for minimizing the load balancing basically. And from all these figures, it's quite evident that the proposed QBCSSA approach, minimizes, the factors such as this particular make span, response time, power consumption, as well as this load balancing, and also improves the degree of VM utilization as well over other compared algorithms as well. So last one that we have to move into the conclusion part, and in the conclusion part, the problem of the task scheduling and the load balancing fall under an NP hard problem. So in order to address these two set of the problems, we have devised many improved meta-heuristic as well as this hybrid algorithms as well, and all these algorithms are also validated against some of your improved quality of service parameters as well as this conflicting scheduling parameters as well. So out of all this, this QBCSSA outperforms among other aforementioned meta-heuristic and hybrid algorithms as well. And if I talk about the future scope, then this load balancing algorithm could be extended in order to design a more scalable as well as this in order to tackle the unpredictable nature of the workloads. And our proposed algorithms do not consider the constraints such as the priority, fault tolerance, capability, delay, and the associated cost. So these parameters could also be considered in order to evaluate the performance of this particular systems. So these are the set of the references that we have taken into consideration. And thank you for your patience and have a good day.